Hi folks, I am John Gallagher and I am a part of Team E65. My teammates are Connor Flack, Logan Manderly, Aaron Whitaker, and Mike Lenner. The five of us created Feed It, an Internet of Things connected pet feeder. At a high level, the goal was to create a device that could remotely feed pets on a schedule while tracking parameters related to food and water. Aaron will explain more of the functions and requirements on the next slide.
The ultimate goal of Feed It is to provide customized assistance to pet owners that need help, for whatever personal reason, to maintain a timely nutritional feeding balance. Our focus is to provide a product that allows any demographic of customers to utilize all the benefits that Feed It can provide. Our design was able to solve the customer's dilemma by having the ability for the customer to control the amount of food as well as dictate the exact time that the pet needs to be fed. The customer also receives several other features that make their life easier when it comes to feeding their pet. Due to the current circumstances of the pandemic, we were not able to achieve all of our target specifications. However, we were able to provide a working prototype along with elaborate theoretical design with individual components tested and functioning properly. Through this experience of creating a product that helps others came important experiences that allowed our team to find the value of diverse strengths in people. Understanding how mechanical, electrical, and software systems all work together was the main key to developing a complex system that has a plethora of subsystems. Most of the people interviewed discussing the aspect of this project were the pet owners who work full-time jobs and usually have children. It was an overall consensus that Feed It would be a comforting resource to rely on when your out-of-control events happen and a pet owner is no longer to be at home and present to feed their pet on time. Another demographic is that the design has become tailored to is the elderly population. As people grow older, they tend to become more forgetful, but this should not prohibit elderly people from having pets. Pets are such an important and life-giving companion that if we can come up with a solution to ease some of that responsibility of owning a cat or dog, then we believe that Feed It should comply with this part of the population of pet owners too. Ease of use is by and far the main standard that this product is aiming to achieve. We are able to comply with this standard by having a very simple to use app that only has a few settings that the user will only need to change whenever they want to. Then to actually work the product, it is just one easy button to perform the action of the product actually feeding the pet. Even further, with this new update of having an LED light, it gives some visual indication of when the food and water levels are low, so that there is a warning before you actually run out of food and water for your pet, and they're therefore unable to feed your pet remotely. Another general standard is the size of the actual product. It is unreasonable to ask people to put an enormous product in their household, taking up too much room in their home. Therefore, we created a prototype around a more compact design as to not take up any unnecessary space. And finally, the appropriate proportions of food given to the animals is another important standard for a consumer. Too much or too little food given to the pet can result in an unhealthy nutritional diet and contradicts the purpose of our product. This is why we have stopping procedures for the food system and the water system, which amounts dispensed can all be set customized on the customer's app.
To meet our customers' and their pets' needs, we decided to start a design from scratch using the customer needs as our design requirements. In order for our design to meet these requirements, we knew we would need to design solutions mechanically, as in the physical structure, including storage and mounting for electrical components. Furthermore, we also had to design electrical solutions, including sensors for data input to act as thresholds for control of the system, motors for movement of mechanical structures, and a way of providing information to the user. Lastly, we knew we would need to create an app that allowed for customer ease of use and remote control of the system for the customer's convenience. Thus, our requirements for the design were to be able to dispense dry pet food and water on command or on a specified schedule, Provide indications to the customer via LEDs and the app with information regarding their pet and the system itself. Provide for system use from anywhere using the app and to prevent food stealing between pets. On the right side of this slide are some of the solutions we used in this design, including its electrical, mechanical, and computer engineering aspects. These are all discussed throughout the presentation.
In terms of mechanical design, we designed it to be easy to reproduce, aesthetically pleasing, functional, and easy to be cleaned. The mechanical parts are shown on the right-hand side of the slide and show what material, what subassembly it is a part of, and the size of the part itself. The food assembly includes the auger, the trough, hopper, one bowl, and one scale. To put it together, you will first need to glue the magnets in the 8 given spots underneath the hopper and above or on top of the trough. These magnets allow the hopper to be securely fastened to the trough but also easily removed so it can be cleaned and refilled. Next, you will want to secure the motor on the back side of the trough by sliding the shaft of the motor through the back hole and then secured by the 4 screws. Next, slide the auger through the trough hole, the large trough hole in the front of the part, and make sure it is connected and secured to the motor shaft so that when it spins there is no slipping. The water assembly consists of the water tank, hose barb, and the hall sensor float. First, you will attach the hall sensor float on the inside of the water tank, followed by screwing in the hose barb on the bottom of the tank. Make sure these screws are tight and that there is no water leaking. Then finally, to put the whole thing together, you will first put the food on the right side of the inside of the housing part, then slide the water tank through its respective column on the left side. Then you'll put the scales on each given hole and then the bowls following on top of them. After that, you will slide the garage doors in its respective rails of each door and then connect the motors to the garage doors so that they can be opened and closed. Finally, to top it off, you will put the feed IT lid on top that has the power and low food and low water light onto the housing itself. It will be connected on the back by a piano hinge so that it can be opened up and then the food tank and water tank can be removed to be cleaned and refilled. Now on the bottom right hand side of the screen you can see what the assembly does that I have just talked about. Then briefly to go over some changes in the mechanical design is the food trough. The picture on the left side was from the fall of 2019. The picture on the right side was from the spring of 2020. As you can see, there are some major changes to the design itself. The reason for some in the spring 2020 is we added the sidewall so that the food would be directed to the sides and on the top of the auger itself instead of just the very top from the first example. And then the slit in the hopper itself is on the hopper for the spring 2020 model, and it starts from the back and the food gets pushed to the front instead of starting at the front, pushed to the front. This allowed us to have more food in the hopper itself and it makes for a better flow. We also added a better motor mount on the back so that it can be secured by screws and not duct tape. And then we also added the 2 tabs on the right and left hand side of the 2020 trough so that it can detect when low food is there. There are many more examples, but they can all be found in the paper. The drafts shown on the right side are the actual CAD draft files of the parts we made for the project. The geometry of the food tank consists of a 4.78 inch by 4.15 inch base with a 6.92 inch height. The overall volume was 137.27 inches cubed, which equated for 9.5 cups, which hits our target for anything above 8 cups that will sufficiently feed an animal for an entire week. The water volume is a 3.75 diameter tank that is 6.11 inches tall, and we equated the volume to be 67.44 inches cubed, which is roughly 5 cups of water, which also would last an animal for an entire week. The overall size of the actual housing is 10 inches by 8.5 inches for the base and 12 inches tall. This included having all the internal electronics in its own compartment, its the own food assembly, its own water assembly, and bowls and scales all into one box, one cubicle rectangle box.
The hardware in this design can be broken down into 6 subsystems. The first subsystem is the load cells. Using load cells, we are able to measure how much food and water are left in the bowls. This allows us to know how much to dispense, as well as to track how much the pets are consuming. Using the HX711 instrument amplifiers, the analog signal is amplified and converted to digital before being sent to the ESP32 microcontroller. The next subsystem is the food storage and dispensing. Since the design allows for storage of food, 2 IR sensors are used to indicate if the food storage is low for the customer's convenience. This is done via an LED as well as in the app. To dispense the food, a geared 60 RPM DC motor spins the auger, which pushes the food out of the hopper and storage and into the bowl. A MOSFET is used to control the motor's dispensing via the ESP32. The next subsystem is the water storage and dispensing. Like the food, the design allows for storage of water. A Hall effect switch works with a float magnet to alert the customer when the water storage is low, also via an LED and the app. To dispense the water, a gravity-fed solenoid valve is opened up using a MOSFET as a switch, controlled by the ESP32. The next subsystem is the RFID. Using the SM130 RFID module and a 13.56 MHz antenna, the system allows the customer to have covers over the food and water unless a pet with a programmed RFID tag is close enough to the system. This module communicates with the ESP32 via UART. The next subsystem are the bowl covers. Using a BJT pair and 2 more DC motors, the doors can be opened and closed via signals from the ESP32. This is done in tandem with the information from the RFID subsystem. As mentioned, the ESP32 is the brains of the system and it controls all of the information used in it. Through these subsystems and with the mechanical system, the customer's needs are met.
One of the most important hardware design choices that we needed to make during this project was what microcontroller would be at the center of our system. Microcontroller was a very important design choice since it's at the center of everything that's going on. First semester for our design, we used a PSOC4 and an Arduino. These were microcontrollers that we had readily available and were already using for other projects and had some knowledge of. This worked well for an initial prototype. However, we realized moving forward we would need to choose one singular microcontroller that more fit all of our hardware specifications that we needed, as well as the other specifications we needed to fit our customer needs. Some of the important considerations that we needed to keep in mind when analyzing different microcontrollers were the operating voltage, what support was out there on the internet for understanding how to use these devices, how much processing power each microcontroller had, how much pinout that each microcontroller had, and what sort of pins it had available, as well as what was available for Wi-Fi connectivity since this was an IoT project. Another important consideration was cost, since we needed to deliver a product that wouldn't cost too much to our consumers. One of the first things we looked at was the Arduino. However, without buying outside components, there wasn't Wi-Fi connectivity built into the Arduino, and it was also more expensive than what we were aiming for. The next thing we looked at was the Raspberry Pi. However, this operated at a voltage higher than what we wanted to do for our overall system, and then it also cost quite a bit. The next thing we looked at was the ESP32. This hit a lot of what we were looking for. Since it had the right operating voltage, there was a lot out there for support. It had Wi-Fi connectivity directly built into it, and the cost was very reasonable. We also looked at particle argon, another board that had Wi-Fi built right into it. However, this item was more expensive than the ESP32. So in the end, we decided to go with the ESP32 for our microcontroller.
There are two components to the software used in FeedIt: the software on the ESP32 microcontroller and the software on the app that controls the ESP32. These were developed side by side because the app and ESP software depend on each other. The ESP has the following libraries to aid in its tasks: ESP Async Web Server, Async TCP, Wi-Fi, and Time Master. Time Master is used for scheduling automatic feeding intervals. But note that the other 3 out of 4 of these libraries are related to networking. This was because reading the inputs from the sensors and sending outputs to the motors are both things that the ESP can do natively. On the networking side, the ESP runs an asynchronous server. This means that incoming and outgoing packets do not interrupt other functions on the ESP. This is important because the water bowl or food bowl could overfill due to a lost packet if it were a synchronous server. This server links to a domain on the internet, but if you typed it into an address bar on a computer, nothing would appear. This is because the server does not run a web page, it merely uses the domain. Also, the ESP requires port 80 to be opened on the router it connects through. Port 80 is the HTTP port. This is used for web pages. Thus, a web page would be an easy addition for the future since the backend for a web server already exists on the ESP. An HTML file or a PHP file on the ESP is the only thing necessary to enable this. Also, nearly every home router made since 2008 can fulfill the networking requirements, so FeedIt is flexible to a home user's network. Here on the right is a screenshot of the input parameters for the asynchronous web server. The only parameters that need to be changed on the ESP for the end user is the router SSID and password. The ESP requires a local static IP address, but this will not be a problem. The setup of FeedIt requires the user to restart the router already. As long as there is nothing else on the network that requires the exact same IP address, there will not be a problem. In reality, since the vast majority of devices use dynamic IP addresses, very few people would have a problem. For regular operation, all the user needs to do is plug it in. It will be ready for operation within 10 seconds. If for some reason the wireless network goes down, the ESP will need to be powered off and on again. On the left, there is a screenshot showing the code on the ESP32 that handles some of the buttons that can be pressed. Every button on the app must have accompanying code on both the ESP32 and the app. On the right is a screenshot of the code used to make the buttons on the app. This button sends a request to the HTTP domain, where it is sent through to the user's router, received by the asynchronous web server on the ESP32, and only then is the request handled by the code on the ESP32 as shown on the left. The only tasks that the app needs to perform is sending requests to a domain. As such, most of the code on the app is for aesthetic purposes, since its goal is to be the user interface. In recognition of dark mode for its improved readability, we have selected that to be the default. In addition, if the request from a button is not received by the ESP32, the app recognizes the error and will display an error message. In the middle of this slide, there is a screenshot of likely the most common error message: connection error, no route to host. This code was developed on DroidScript, a development platform centered on an Android phone. A computer can connect into the phone and control the app development over a wireless connection. This is advantageous because changes in the code can be seen on the app in real time. When the changes are deemed satisfactory, the app allows the code to compile into an Android APK, the file type of Android apps. This app requires users to have an Android phone running Android version 4.4.1 KitKat or newer. This condition will be satisfied by most phones made after 2013. Since the app is relatively simple due to how the functions are handled on the ESP, making an accompanying app for iOS or even Windows Phone would be seamless. In addition, adding additional functions on the current app would be trivial as well.
One of the big unforeseen events this semester was, of course, COVID-19 and the implications that had on our project. We were no longer together as a team to work on our project, as well as having all the resources we needed to do everything that we wanted to. While all of our subcomponents had been completed, we weren't able to completely assemble everything as we would have liked and to complete all the testing and refinement that we would have liked once all the subcomponents that we had already proved worked were together. For example, the motors on the garage door were controlled with an H-bridge circuit. This allowed the motors to go both up, down, and to be stationary. However, we weren't able to rigorously test the circuit and see what changes needed to be made. Another aspect that we weren't able to do due to COVID-19 is other refining testing. While we had proved individually that all the concepts of our project worked, there was some refinement that we likely would have done if we were able to all be together. For example, we had noticed that when filling the food bowls with our dispensing mechanism, that they consistently overfilled. Part of what we would have done if we had more time to refine this project would be to run multiple tests to figure out why this was happening and come up with a control solution so the bowls would fill to the correct amount. This likely would have been done by some sort of proportional offset since it was consistently overfilling. This may have been a function of how much food was commanded, or it just may have been a consistent amount each time. Once we would have determined that, we then could have refined some controls to be able to accurately fill the bowl each time. While we proved that our load sensors worked to stop at a weight to fill the bowls to, we still would have liked to refine our system. These are just some of the examples of how the scope of our project changed because of COVID-19.
Bingo.
The embedded video on the slide is of last semester's prototype, which has since been overhauled to the present design. Since we were not able to 3D print and assemble the new design, we do not have a video that shows it. In this video, notice that both the food and water are dispensed until a specified weight is reached by the load cells. The pictures on this slide show some of the key updates made to the electrical subsystem. On the left, the ESP32 is shown with the up-to-date I/O and the connections to the load cells. On the upper right, a close-up of the ESP32 is shown. This microcontroller replaces both the PSOC4 and the Arduino Uno used in the previous design, allowing for much cleaner wiring. On the bottom right is the SM130 RFID module with a 13.56 MHz RFID antenna. This is a completely new addition to the project this semester and allows us to prevent food stealing between pets. When an RFID tag is placed on the pet's collar, the bowl covers will open only when the pet is close enough to the system.
The cost analysis from our project includes the cost per unit, labor cost, and the sales forecast. The cost for the prototype would be roughly $1,163. Majority of these costs stem from 3D printing. The reason the cost is so high is because we would need to contact a third party to print these items since they are so large. Printing these one-off items is very expensive, while 3D printing in general is very cheap. If you were to print in bulk and in-house, this would reduce the cost tremendously, as shown as in our wholesale cost pricing. The 3D printing would go from roughly $900 all the way down to $6. This is because SLS plastic weighs about 0.0012 grams per cubic inch of material. And when you buy SLS plastic for 3D printing, on average, it costs 40 bucks for 1 kilogram of material, which is around 2.2 pounds. This means that the once $395 hopper can now be sold or printed in-house for $2.73 in material alone without including the labor. Adding in the labor, we have 5 engineering positions, which equate to the 5 people in this project, as well as manufacturers slash 3D printing people that will be able to keep the machines moving and making sure they are working. If we reduce the salary to a per unit basis, which is a standard 40-hour work week and making 3 units per day, it'd be on average, it would cost 64.92 in labor per unit, bringing it to a grand total of our cost of our unit is $273.28. From surveys in the beginning of the year, our target audience said they would be willing to pay upwards to $350. However, if we were to sell this product at $350, our percent margin ratio would be way too low and it wouldn't be a successful business. If we were thinking at this as a successful business standpoint, we would have to sell the feed it for around $500. We took this into account in our sales forecast because some buyers might be shocked by the price difference of what they wanted it for how much they have to pay for it. So we took into account that it would be a slow start of units being sold. As you can see, in the first month of April, we would be selling 0 units. In May, it'd be 2, June would be 5, etc. And then once we figure out the processes and find better warehouse items, we will be able to reduce the cost down tremendously, and therefore reducing the price we need to sell it at to still get that profit margin above 40%. Our year forecast has us selling about 350 units and having a gross profit of roughly $54,985.
The following table shows some of the design goals we laid out at the start of this project. These design goals came from our customer needs. If these design goals were met, that means the customer need that it was meant to fill was met. The table shows the various stage that each of these subcomponents was in. Our food dispensing mechanism was successfully prototyped, as well as our water dispensing mechanism and sensors to detect if water and food were low. Basic functionality of the RFID to detect an animal presence was completed, however, it was not fully integrated and refined yet. A garage door system was designed, but it was not yet completely built and integrated into the system. App communications with the device were completed on a basic functionality level with some simple buttons, however, full functionality that we are aiming for has not yet been completed. Overall mechanical housing was completely designed, however, this was also not fully built and integrated into the system. Our cost specification was a little bit over cost, however, we believe if mass produced that this cost would come much further down. The parts of the design goals that were not met were mostly not met due to the fact that we could not complete all aspects due to COVID-19. However, all subsystems were proven to work and completed, and basic functionality was completed. If integrated together, all design goals likely would have been met.
This project in its entirety taught us an insurmountable amount of lessons. The main lesson that we learned was that if you keep a common goal of fulfilling someone's needs, then the rest of the planning consists of the efforts towards achieving that goal. We believe that even through this pandemic that we've been faced with, we continually challenged ourselves and this project to improve its design to better help our customer. Even if we had to work with pure theory, we were always striving to find the best process to complete our product that can reach our target specifications. We also learned how important it is to find each teammate's strengths and allow them to create an idea to which the rest of the team can provide support and constructive criticism. Some things that worked well were the strategy to always be willing to readjust the CAD based on some unchangeable electrical components. The CAD could be designed so that we wouldn't have to sacrifice our goals and the customer needs. Then all that would have to be addressed was the physical materials that it would take to actually create the newly designed product. Some things that were a bit tricky were the RFID tags. They seem to be a little bit more difficult to implement than the other sensors. However, using the RFID tags does provide a lot of online support that can be found and tailored to fit the exact specifications. If there were teams that wanted to continue this project, we have a few recommendations. One would be to spend more time working with the app and allowing a significant amount of time to get the communication between the app and the ESP32 to establish a solid connection. Another is to find a router to use because any protected Wi-Fi makes finding that connection a lot more difficult. Since we were unable to follow through our project to completion, we weren't able to form a more elaborate compilation of recommendations for future iterations of this product. However, we believe that our theoretical design gives a very strong base for anyone else to take this project to the next level.
Thank you for taking the time to watch our presentation of our senior design project. If you have any questions, you can direct them to any one of the team members at our school email addresses. This slide gives references for materials used throughout this presentation, including images and other resources.